Hello, everyone. My name is Pramika Garg. I am one of your fellow scholars from the SUSE Foundation Scholarship. I'm here to help those just at the finish line get a boost and complete Lesson 5 and hence the entire course. So let's get started. Here we shall look at CI or continuous integration. So, what exactly is continuous integration? Continuous integration is a development process in which developers routinely, usually many times per day, integrate work into a common repository. An automated build and automated tests may then be used to verify each integration. While automated testing is not a requirement of CI, it is frequently assumed. One of the main advantages of integrating on a regular basis is that you may discover and locate problems more rapidly. Because each modification is usually minor, identifying the particular change that caused a fault may be done quickly. Continuous integration (CI) is a process for creating an application bundle that can be distributed to users. As a result, if a commit to the main branch satisfies the anticipated behavior, it is built, tested, and packaged. The outcome of continuous integration in the cloud native environment is an OCI compliant Docker image or artifact. It is a process of merging changes from various team members into a mainline as soon as feasible, ideally many times each day. This ensures that the code that individual developers work on does not diverge excessively. Continuous integration, when combined with automated testing, may make your code more dependable. So now that we have understood what is continuous integration, let us take a look at three of its main sections. The build stage is the first stretch of a CI/CD pipeline, and it automates steps like downloading dependencies, installing tools, and compiling. Besides building code, build automation includes using tools to check that the code is safe and follows best practices. The build stage usually ends in the artifact generation step, where we create a production-ready package. It includes the following steps. Number 1. Compilation. Step 1 of the build stage compiles the application. On compiled languages, it means that we can generate a working binary, whereas on interpreted languages, we confirm that we have the required dependencies and tools to successfully build the application. The result can be a binary file, a code tarball, an installable package, a website, a container image. The main thing is that we have something that we can run and test. Number 2, linting and code analysis. Discipline is required when programming. We must tackle issues while adhering to best practices and a consistent coding style. You can keep bad code at bay with the aid of automated analysis tools. Linters improve code quality by highlighting troublesome and difficult to maintain elements. Linters employ a set of rules to establish a consistent standard that benefits the team's readability. Metrics are used by the quality tool to identify areas where code may be improved. The number of lines, documentation coverage, and complexity level are among the metrics gathered. Tools for security analysis scrutinize the code, mark sections that may be vulnerable, and ensure that dependencies don't have any known security flaws. Number 3. Artifact generation. The last step packages the application for release or deployment. The released package will include everything needed to run or install the application, including application code, installation scripts, dependencies and libraries, application metadata, documentation, and license information. Scalability. An unavoidable component of software development for firms aiming to expand or grow is enabled through automated testing. In reality, there is no good reason not to use a CI/CD pipeline to automate testing. In CI/CD pipelines, automated testing plays a function that is as adaptable as the pipelines themselves. Furthermore, manual testing is not as flexible as automated testing. CI/CD automation allows teams to undertake a wider range of tests with greater ease. Tests like API testing, load testing, UI testing, regression testing, unit and component testing, functional testing, non-functional testing, and cross-browser testing can be utilized. Number 3. A software package is a downloadable file that may be loaded on computers, servers, and mobile devices. Consider .exe file for Windows, .dmg files for Mac, and .rpm or .deb files for Linux or Debian systems. These software packages are available in several formats as well as a variety of metadata descriptions. It has 3 common steps: write code, define metadata, and archive code and metadata for distribution. The third step mentioned above, archiving code, creates a software package for release. This archive or artifact is distributed to repositories at a release stage. The actual package construction procedure differs depending on the package type. Package types span from operating system level packages to packages that execute front-end code in browsers, with each one having its own architecture. To create that package from source code into an archive for distribution, each package type has either a tool or a specialized procedure. The npm pack command, for example, will archive the code base into a tarball that may be used on an npm registry. We did want to manage all of the tasks required to create the package from within our CI server. In the release stage, this method will allow us to upload the package to a repository. In the case of Docker, the packaging stage produces an executable that includes the most recent features as well as their dependencies. Docker's Docker build and Docker pusher commands are used for implementing this stage. These scripts use a Docker file to produce a Docker image and save it to a registry like Docker Hub. So I hope this cleared up continuous integration and its subparts for all of you. I wish you all the best in finishing your course. Let's make it happen. This has been Pramika Garg, a fellow scholar from the SUSE Udacity Foundation's Scholarship Program. Thank you.